Okay, hello everyone, and welcome to the Civil Seminar. Today it's really a great pleasure to have Dr. Sorooshian with us. It's really not easy for me to introduce him, but I'll try to make it short. Dr. Sorooshian is a distinguished professor of civil and environmental engineering and Earth System Science at the University of California, Irvine. He is one of the most influential scholars with groundbreaking contributions in hydrology, climatology, and remote sensing of precipitation over the past 40 plus years. Dr. Sorooshian's research is focused on surface hydrology in the early area of rainfall runoff modeling, model identification and calibration, characterizing the uncertainties of calibration data. He has great contributions in remote sensing of precipitation, including the development of the widely used PERSIANN remotely sensed precipitation product, and the application of remote sensing data to characterize hydrologic parameters, as well as other areas, the climate variability and change and their implications for water resources. Dr. Soroosh has received several prestigious awards, and there is certainly no time to mention them all. These include the NASA Distinguished Public Service Medal, the Robert Horton Memorial Lectureship Award from the American Meteorological Society, the Prince Sultan Abdulaziz International Prize for Water recipient, and in the same year he was named an honorary professor by the Beijing University. In 2013, he received the Robert Horton Medal from the American Geophysical Union, and in 2017 he received the Venti Chow Award from the American Society of Civil Engineers. Dr. Soroosh has trained hundreds of students, including my PhD supervisor, Dr. Moratani, and many other researchers and scholars who are now leading professors and scientists at UCLA, University of Arizona, NASA, among others. So he's definitely an exceptional role model to his students and other young researchers, including myself. With that said, I would ask Dr. Sorooshian to please present his lecture on the role of hydroclimate modeling for regional water resources planning, expectations, promises, and reality.
Well, thank you very much, Mohammad Reza, for the kind words. I truly appreciate that. I'm humbled by it. And well, everybody, I'm so happy to be invited and participate in this. In the way of background, I actually started my educational career as a mechanical engineering from a school in California, Cal Poly San Luis Obispo, mechanical. Then I went to UCLA in operations, research, and systems, and then finally water resources. All of that by accident because I wanted to be an aerospace engineer, but ended up as a hydrologist. That remains for a different discussion on one's life and history. But I went to Case Western Reserve University, my first faculty job, not too far from where you are relative to where I am now, for 5 years, and then 20 years, University of Arizona. And since 2003, I've been here at the University of California, Irvine. So without spending too much time, I'm gonna switch to my talk. And let me see, I just got a notice to send degree programs, but anyhow, I'll get rid of that. So the topic, as Mohammad Reza pointed out, let me just start. Let me see if I can reduce the, yeah, so I get that. introduced, I thought I'd talk about the role of hydroclimate modeling. My original work was mostly with hydrologic modeling and parameter estimation. But today I decided to talk about where I see things. I guess at my age and after 40 years, I have some personal perspectives that you don't necessarily have to agree to, or but I express them. So these are the various funding agencies that support our work. And let me just activate my pointer. Yeah, these are the various agencies in the United States that have supported our research. And as Mohammad Reza mentioned, I'm at the University of California, Irvine, which is one of the 10 campuses of the UC system. And we are about 60 kilometers south of Los Angeles, UCLA, and a nice place. We are about 33,000 student body. Of the total University of California is 250,000. Always like to have a little introduction of the people that have played a key role in my group over the years. And maybe this last row represents the current students who have recently graduated or are still in the program. All right, getting to the story of what I want to tell you, it's always about the relationship of climate with hydrology and how it impacts water resources. And the type of questions that one receives these days is, how will climate change affect precipitation variability and water availability? In general, water resources, but since I focus mostly on precipitation because all the natural disasters such as floods and droughts are as a result of plenty of precipitation or lack of it. And the second question one can get is, can we predict the future changes which are responsive to user needs, not just for academic purposes and publishing another paper, but who cares about them? So, okay. As far as the relationship between climate and hydrology, when you warm up the ocean, the physics is pretty straightforward. When the temperature of the earth increases and you warm up the ocean, you essentially result in more evaporation to take place because 3/4 of the planet is covered with water. And also the water holding capacity of the atmosphere with the increase in temperature increases. That means roughly for every 20°F increase in the air temperature, you double the capacity of the atmosphere to hold water molecules and particles. So what goes up must come down. And also you have to know that water vapor itself is a greenhouse gas and has a greenhouse effect on the climate system. And that's why the role of clouds, which have mostly water moisture, is really important in regulating the climate. If it was left to be natural, not methane and CO2 that are known to cause all kinds of other problems. So one thing that has been established, that the hydrologic cycle of the earth has been intensified. And as a result of that, we are seeing more extremes, either floods or droughts. And the news is full of stories about which area of the world has been affected by droughts or severe flooding, as recently we've seen it in many places. So essentially we have two water resources and hydrology challenges dealing with the hazards, and the other one is water supply requirements, both in terms of the quantity and the quality. So what are some of the stresses on water resources and the related ecosystems of our planet? Our number one, population impact. That one is more predictable because demographers are pretty good with their models to try to project the population of the earth and into the future. But when it comes to climate impact, unfortunately, it's less predictable, even though quite a bit of advances have been made, and we'll talk a little bit about that. As far as population is concerned, I'm sure you may have seen this graph put by UN some years ago, which essentially identifies the mega cities. The key thing to take from this story here is that the urban population in 1970 was only less than 40%. By 2010, it was half of the world population were living in urban areas, and the red dots represent cities and mega cities depending upon the size, and you see mostly in the ocean and Indian subcontinent is where you see huge growth. What is also interesting to note is that it took about 200,000 years of human history for the world population to reach 1 billion, okay? And only 200 years more to reach 7 billion plus, which was reached a couple of years ago. And demographers predict that by 2025, we may reach 8.3 billion. So more population obviously requires more water resources, food, etc., and that's where the stresses come. Also noteworthy is that about 44% of the world population, roughly speaking, live about 150 kilometers from the sea and the coastlines. And that, of course, brings its own challenges, particularly with respect to the groundwater and seawater, saltwater intrusion, etc. But also creates opportunities for desalination, which has a plus and a negative. Technology is there, but of course, it's highly energy consuming technology and adds to the greenhouse gases. Distribution of fresh water, globally speaking, and we've chosen a number of these countries. The pie represents the amount of water used. Green represents agriculture, yellow represents domestic, and blue represents the industry. So as far as US is concerned, roughly half and half. I should have added Canada, I apologize, but I'm sure you guys have a good idea of what the distribution is. So as you see, let's say China, India, Iran, and even Brazil, the dominant user of water is the agriculture. If we look at the states of California or Southwest United States, almost 80% of the total amount of water used is in the agricultural sector. So these requirements obviously are putting stresses, and especially when we have periods of drought, etc. So what we have done as humans to deal with these issues, and it's nothing that you don't know, but I'm going to repeat it again, to deal with both water requirements, water resources needs, and address hydrologic extremes, has been through engineering approach, which is, I'm speaking to the right group. We are mostly engineers, and we should take pride in what has been accomplished and also recognize some of the things that probably have been the negative consequences of the developments. So we usually build structures to control, store, and then we have the ability to pump and transfer water to where it's needed. And good examples of those are in the Southwest US, such as the Central Arizona project, which takes water out of Colorado River for the central part of the state of Arizona. We have the California Water Project that brings water to even Los Angeles area. So the engineering aspects have been well established from thousands of years. This is an old dam near the city where I was born in Kerman, Iran. That is, nobody's done really any analysis, but the guesstimates are somewhere between 500 to 800 years old, built with the whatever engineering technologies they had, using eggshells and gypsum in order to put these blocks of stone together and make a dam. As compared to today, we pour a lot of concrete and make these incredible structures, such as the Glen Canyon Dam on the Colorado River, which has got the Lake Powell behind it. Romans built aqueducts to essentially allow water to take advantage of the gravitational flow. and move it from where it was available to the cities that required it. And if you've gone to Rome or any place in that part of the world, or even in Middle Eastern countries, you see examples of these kinds of ingenuity to make sure that it allows water to flow with gravity towards where it's needed. And nowadays, as I said, we have structures like this one in the Colorado River taking water to Arizona. Interestingly enough, when this project, Central Arizona project, was initiated, it was pushed by the agricultural sector in the state of Arizona 20 years later, and $2 billion worth of investment. When the water got there, ag people decided they didn't want the water because it was too salty, and they preferred to take advantage of the groundwater they had, so they made it to be a problem for the cities. So, here is a good example of what was to be turned out not to be. And but anyhow, that's a challenge the cities of Tucson and Phoenix are dealing with. Dam building in the United States has an interesting history. And from 1800 all the way to 2000 or so, more than 70,000 dams built. But from the late 60s, late 60s, 70s, it slowed down. And by 2000, I don't think any more dams have been built in the US. China now has surpassed 95,000 dams and still adding more dams and structures. Groundwater, one of the key elements of the water resources, innovative tools and technologies by the Persian Empire thousands of years ago that dominated this region of the world was to create canals, and through a mother well, reaching the aquifer and connecting these different sections through different wells, and essentially allowing nature to provide water to where it was needed. But unfortunately, with the advent of better technologies such as drilling systems, you now can go and drill a well as deep as you want to if you have the money, and start pumping the water out of the aquifer system. And that has been a big disaster, particularly in many regions of the world, including California, but regions such as Middle Eastern countries have seen an unsustainable depletion of the groundwater aquifers. So what are the expectations? To provide useful, relevant, and reliable information for operational planning and design of water resources systems. That's expected of us. It's expected of us in academia, in research centers, in operational centers, to really do what we can best in order to allow better and optimal use of the resources and tackle the needs. So what do we rely on to create these kinds of informations and improve models? It's through observations and use of model and projections by the models. Observations, we come in different form. We have in situ observations, ground-based observations. We have remote sensing nowadays. And we have proxy records that rely heavily on the advances made in the chemistry field of isotope analysis. And there are good examples of those of analysis of ice cores and getting a history of CO2 for 200,000 years through air bubbles in the ice cores, but also for detecting droughts through tree ring analysis, as well as dry lake beds, and I'll talk about that. The other part is models. We have statistical methods and we have physically based models, which are the hydroclimate models or the hydrologic watershed models. Addressing extremes in water resources planning, let me tell you that we are all familiar with statistical hydrologies, and a good number of Canadian colleagues have contributed immensely to the field of stochastic hydrology. So I'm sure that at least in my days, we were asked to go and collect, get some data from US Geological book and do an analysis and come up with the return period and get the flood frequency analysis done through a semi-log paper. So that's known as the traditional statistical hydrology, which is now the backbone of a lot of the planning that happens, even floodplain mapping of 100-year flood, 20-year flood, and design of structures based on statistical hydrology. So it's pretty straightforward, I guess, now that you think of it, is that you have the information from a given gauge, and the longer the better, because that captures the statistics better. And if you use partial duration method or the annual series method, in this case, partial duration, just the cut through there, anything above that is considered as part of the data that is considered to be extreme. You fit a probability distribution, and as you know, log Pearson type 3 is kind of the standard, which has been adopted by most places in the world. And then from that probability distribution, then you generate, and this is known as synthetic hydrology. You create a lot of scenarios of floods, and you go from there, okay? I don't know why I get something on my screen and it slows things down. All right, so statistical hydrology was based on the assumption that nature behaves in a stationary manner, and that means history has a tendency to repeat itself, and the distribution that you developed for this part of the record that you had was the basis of coming up with the statistical methods to generate future scenarios. Well, we know with climate change, this might not be the case, and research slowly but surely is trying to address that, and non-stationarity is only an assumption. It's not that everybody believed it was there, is going to be something that has to be dealt with. So what's happening here is that if I have a river basin and I have gotten the data from the river, Mississippi River, or name it Nile River, etc. I plot it on a semi-log paper, and based on that hypothetical, I come up with a 100-year flood scenario based on my statistics and the probability distribution that I have. Two things are likely to happen under climate change scenario. One is that we will see more variability to take place, or less variability. And if there is more variability, the nature of your 100-year flood is going to change. It's not going to be the same magnitude, may happen more frequently. And as such, this is where we see the impact of the changes that happen. Similarly, if a region becomes less variable, and then the statistics favor you in a sense that the storm that used to be 100-year storm is now going to be maybe 700-year storm. So these changes, variabilities, are really something that we see that the infrastructure that was designed based on those statistics may no longer be adequate, as we see a lot of damage happening because these systems and drainage networks were insufficient for the amount of water that now is being generated. Furthermore, as you urbanize an area, you're also going to be experiencing similar things downstream. And okay, well, I jumped the gun too much, too fast. Sorry. And you urbanize a region, and then you will see that, in fact, as a result of that, you essentially increase the amount, the volume of the flow as a result of a similar storm. And as such, if you had a distribution developed based on the past history, and less urbanized area is no longer adequate. So that's on the statistics side. There's still the backbone of a lot of work in engineering design, but then we have new kids on the block, and particularly models. We now have to deal with the reality. What is the current state of model projections that are relevant and useful for water resources planning? So we require three types of information if I break them up. One is short term. This is for flash floods, the hours to days. Information is required mostly at the weather scale. The second group is at the seasonal or mid-range, which is up to 3 months. That is used mostly for reservoir operations and short-term planning. And last but not least is the long-term and long range, which is decadal to centennial timescales. And building a major dam with billions of dollars of investment, you better do your work and decide you don't want to over-design or under-design a structure for the region of interest. So that's the range of data that you need for today. I really focus on the mid-range and the long range because hydroclimate was the focus that I chose. We see a lot of work done on the climate modeling side, this is essentially a practice of taking the output of a climate model, downscale it to a regional or watershed scale, and use that information to do scenario analysis and try to take advantage of models in terms of assisting you in your future planning. So, you know, different methods have been approached. There's statistical, dynamical approaches. The ensemble approach is that you take a bunch of different models because you don't want to put your trust in one model and initialize them with the same boundaries and initial conditions generated by a climate model grid. And in that case, model 1, 2, 3, 4, 5, 6, and each of them you allow them to operate and generate their scenarios of precipitation from a water resources point of view. I'm interested in the rain that is generated by the models. And then after that, you put these information together to create an ensemble of scenarios for the watershed or river basin of interest. Then you take this ensemble and over your region of interest and pass it through a hydrologic model, whether distributed, lumped, it doesn't matter. And then you generate a sequence of future scenarios of flows that could assist you in designs and operational purposes. So the question goes back to the original premise. How good was the climate model output that generated these scenarios for me in the future that I fed them into my hydrologic model? So the title of this section of my talk is what do climate models tell us about the future, okay? So I talk first about mid-range forecasting, which is this known as the seasonal scale. One of the centers, and there are many, Canada has its own centers, but the one that I use them as an example is what is known as the International Research Institute, IRI. They have a number of products. They're located in New York, in Lamont Doherty Center as a part of the Columbia University. And IRI originally was intended to be an international research institute, and they thought that other countries will bring money to this center to work together, but at the end it turned out they said, well, why do we have to give our money to a center in the US? And it didn't work that, but the government here is supporting it. So if you go to their website, one of the products they have, it's called an IRI multi-model probability forecast for precipitation. And they generate a probabilistic estimate based on an ensemble of models of 20 or so plus models. And they come up with these kinds of maps, which is probabilistic in nature. It says probability of most likely categories. This is based on probability statements. If it's in the cooler colors, that means those regions in the extreme are likely to see more precipitation. and the warmer colors show the areas are going to see less precipitation. So I use this as an example. This was their projection in 2018 December for January, February, March, and I isolated two regions. One is Southern California here, and the other one was Iran, which is the country that I was born in, and Mohammad Reza comes from there, and maybe a number of you as well. So the key is that that was the projection. So you don't expect to see much changes over the Iranian plateau, and you expect to see dryness over the Western United States. It turned out that in that particular year, January, we had one of the wettest seasons in the recent history of California. So everything was just the opposite. So was in Iran. In the January, February, March framework of 2019, tremendous floods happened in the western part of the country. So all I'm saying is that not to blame the center, but that's the nature of the game. The complexity of our systems are such that it's not that easy. So if you wonder what is their projection, I downloaded this yesterday. This is their forecast or projection generated a few days ago, in February for the month of March, April, and May. And you will see maybe in Canada, in your region, maybe you're lucky. You're seeing maybe a little greener areas. Bad news for us, but we will know more when May passes and see how much it changed. And the same goes for other parts of the world. And it also has limitations. There are certain regions of the world that it actually does not have much forecast. The pinkish area represents this is the dry season. They don't necessarily have to have a forecast for it. Next, I get to the long range, which is really at the climate model scale. I had a wonderful guy, Dr. Miao, who's a professor now at Beijing Normal University, spent some time with us. And we looked at the CMIP5, which are from the IPCC studies. And at that time, 5 years ago, was CMIP5. Now it's CMIP6, and the report will come out soon. But the model simulations are already posted on a number of government computer sites, such as Livermore, that we were able to download these. So the question is, how good are these climate models that are part of the IPCC that countries volunteer and provide their outputs to? Here is for the scenario 8.5, which is really on the supposedly when we follow a Trumpist attitude and decide everything is handy dandy, we should burn fossil fuels and not worry about anything. But the climate scenarios say that by year 2100, we will reach almost 1,000 parts per million concentration, which now we are about 380 or so, 400. And that's the worst case scenario. So if you look at the Western United States, and this is one area that I'm trying to show, you will see that the French model sees Northern California to be wet, Southern California so-so, the Australian model also wet. Then we have the US model that shows we're going to be getting drier in the next 80 years. And the British model is kind of mixed. Southern part is the drier. This is from the CMIP5. CMIP6, you would think that the models have advanced and hopefully we are improving the ability of these models to project. And these are a few other models. Is a Chinese model. I included the Canadian model, the French model, and the Japanese model. And you see that the models still don't agree. If you are a pessimist, you probably take either the Chinese or the Japanese model. And if you are an optimist, you take the Canadian model that projects that this region of the US is going to get wetter. My point is that these climate models are pretty good now in projecting temperatures. They're pretty consistent in terms of their projections, but when it comes to precipitation, it's still all over the map. Some say, well, you know, we ensemble, we average everything out, but you know, that is something that we as engineers could question. 1 plus and 1 minus, what does it get us? You know, increase and decrease, you get 50-50. When it comes to drought, which is really a big issue in many parts of the world, my colleagues Siegfried Schubert, we were in Spain at one point, we came up with this diagram, and reality was that's back in 2011. I don't know how much it's changed. Unfortunately, the ability to predict droughts is very limited. This is the region where, in terms of the time scale and spatial scale, probably have some use. This is where people really need the data. But most of this region is unpredictable, either has low predictability. The only place where we have high predictability scale from models is in the short time frame of no more than a few months, and over very large scale in terms of spatial scale. So these are the limitations. Let me give my take-home message up to this point, which is presently the accuracy of hydroclimate model predictions falls short of meeting the requirements of water resources planning. Hardly used for operational purposes. I don't care who said what, but you know, most agencies don't necessarily use them. They take them under advisement. And it's really not a good idea to push their use while highly uncertain. Coming from a developing country, I'm particularly sensitive to the fact that sometimes these things are pushed down to be used by other countries, by advanced industry or developed countries. And I don't think if they don't use it, why are they pushing it for others to use? So it comes back again to our role as engineers, factoring in resiliency in water resources system design and planning is still the safest approach to take. So what can we promise, or what should be the promises? We should promise and work hard to get better models, improve observations and analysis tools, thanks to, you know, information technology and the capabilities the machine learnings have, the computational capabilities that we have. We can sort through a lot of data and actually see what the data tell us about physics sometimes when you're at a impasse. And also we have to be good and follow engineering ethics, more realistic about what we promise. Don't overpromise if you can't deliver. So first, we talk about observations. Observations are extremely crucial in this game. I already talked about models. Observations are very crucial, and if this is the present time, as I've put the line here, if I look at the past, the planet Earth has a history of 4 billion years. Unfortunately, instrumental data is something relatively new, even in the 2,000-year span of past history. We only have had gauges, river gauges, etc., that could go as long as maybe 100, 150, 200 years for some countries, and some other places even less. Beyond this point is really more constructed through paleo analysis or proxy records, such as I told you, tree rings and isotope analysis on certain things that you can do. Then we have remote sensing. That has been something recent, maybe 50 years of Earth observations, and we'll talk about that. So that's as far as record and historical information is concerned. But the future is based on the models, and I already presented my views of where we are with the models, and hopefully we can make advances and improvements, because that's what we have to promise. I talked to you about droughts. This is from my colleague who was at Arizona, now at Michigan. Overpeck, he's the dean over there now. It's a historical perspective based on isotope analysis of samples from dry lakes in Nebraska or Idaho, I forgot which one, but anything below the line for that 2,000 years represents periods that precipitation was below average. Anything in the greenish area represents times when the precipitation was above average. So as you see, there's something called in the US as Dust Bowl, 1930s, terrible conditions of the weather that lasted for years in Nebraska, Kansas, etc. And there are movies about it. If you compare the devastation that was caused in the 1930s of the Dust Bowl as compared to what radio records show, where we've had mega droughts of 200 years, that pales as compared to these. So we are really the, talk about variability and non-stationarity of the climate. So proxy information can give us some sense of what is going on. So now I'm gonna, for the rest of my talk, which I still have a little time, is to concentrate on precipitation and the importance of estimating and measuring precipitation. This picture I took when I was in Tucson, Arizona from my house. During the summertime, there's a 60-day period, they call it the Southwest Monsoon. A band of moisture from the Gulf of Mexico kind of rotates over New Mexico, comes towards Arizona, moves towards the west, and with the heat and the hot summer there, the moisture is lifted up through convection, and you get beautiful thunderstorms like this one. And of course, the gauging station was at the airport and showed 0 precipitation for Tucson that day. But this storm lasted only 45 minutes with several inches of rain, and some fancy houses in the foothills of Catalinas in Tucson were devastated. So it tells you that really it is an important thing to measure, but it's not only the measurement, but having adequate high resolution, both in time and space observations for not only model input, but calibration, testing, and also capturing extremes. So what do we have in our inventory measuring precipitation? Rain gauges are probably 100 years at max, but technology has improved. They can send the information now remotely via satellites, etc. We have the radar system. Doppler radar has been adapted, and now we have satellites that are helping us. So which one to trust? I guess that's a big question. When you talk about gauges, it would be fantastic if you could put a gauge everywhere, as I show you the example of Tucson. You know, there was no gauge in that area where that storm hit. So it's really the number of gauges and the density of gauges in space that matters. As an example, if you look at China, 1 gauge per 25,000 kilometers on the average for the northwestern, western part of the drier part of China, 2 gauges per 10,000 kilometers square for the monsoon region of China. For the United States, Western United States, is roughly about 1 gauge per 600 kilometers square, which definitely is not the type of density of spatial gauges that will capture the type of convective storms that I talked about. Also, the accuracy matters. Of course, I trust gauges. This is an experimental watershed near Tucson known as the Walnut Gulch. And you may have heard and seen movies of Tombstone, Arizona. That's where it is. And that's the closest it comes to reality. And this watershed, which is done by the Agricultural Research Service in the US, has 1 gauge per kilometer square. So you could assume that this is the closest you come to the truth. Here is a radar, which is about 100 kilometers or 80 kilometers, I forgot, maybe less. That is for the southern Arizona, Tucson. This storm was on August 11th of 2000, one of those monsoon events, where radar captured it this way and the gauges captured it this way. And if you did the analysis, which we did with Efrat Mourin et al., we published this, was 70% overestimation by radar. And physically it's explained because the rain that is falling from the cloud, because of 105-degree temperature of the ground evaporates on the way to the ground, radar picks it up in maybe 10,000 feet above the land, but what falls is not necessarily what you see. So, you know, you have these problems. So where are satellites these days? We got quite a few Earth observing satellites for various purposes, and some of them are environmental satellites that measure information or provide information for precipitation estimation. So let me go back here. So we have three types of satellites, as most of you probably know. We have geostationary satellites that are parked about 35,000 kilometers above the Earth. And why they're called geostationary? Because they rotate with respect to the same location of the Earth. They're synchronized. And so therefore you get full coverage, but from 35,000 kilometers, as opposed to polar orbiting, that is at less than 1,000 kilometers, but unfortunately you get only a snapshot. You have to wait 12 hours later. These are passive microwave, and then we've had a few active radars, such as the one on TRMM and now on GPM. And this is almost like having a CAT scan through the storm. It gets the hydrometeors, and you can really get full details. Again, the problem is that you can't have too many of them, very expensive. But if you do have them, they give you good detailed information, but then once it flies over, you have to wait 12 hours later to go see it. So the active remote sensing sends a signal, and when it hits the water particles in the cloud or in the rainstorm, it sends a signal back, and then you can process this way. The passive one is only based on the radiation the Earth receives and the reflections that you get, and it certainly doesn't provide as much of the same information. So you have to really combine the two in order to hopefully improve your products. The geostationary satellites cover much of the Earth. Each country, many countries have it. Canada and the US benefit from the two, goes east and goes west of the US. Japanese have one, Chinese, Indians, and Europeans. So you put the whole picture of the world together, you get a nice view. And that's what the weather channels show us, the clouds moving, etc. What is also fascinating is that the older version of the geostationary satellites, or the infrared, if you wish to call them, they only had 5 channels, visible plus a couple in the other spectral ranges. The new ones have 16 channels, which really provides you an abundance of new information. And that's where most of my students these days work, is try to see how you can tease out relevant information from these other channels and improve your algorithms. We came up with the PERSIANN system that goes back into the mid-90s. My former student and now colleague here, Colin Xu, was the one to first apply artificial neural networks. And from gathering the information from the IR channels plus the other channels to calibrate the nodes of the artificial neural network to generate products. So what we have at the present time are 3 websites that I invite you, if you have an interest, to go and visit them. You can just Google CHRS UCI. You can go to the website and then choose. RainSphere represents our climate data. iRain represents our real-time weather scale. And then CHRS data portal is where you can get all the data free of charge. CHRS, RainSphere, and I should acknowledge the work of Fu Wen, was my PhD student, and now is an adjunct professor, assistant professor here in our group, who was visionary enough and creative enough to say, well, professor, we need to really serve our data that in a user-friendly. He comes from Vietnam. He obviously appreciates how other countries could benefit from this data. So he took the charge, and with some students from computer science helping him, they developed these websites. Now, our CHRS RainSphere serves the data that we developed for NOAA in the United States, known as the Climate Data Record. They asked us, since our algorithm was based on IR, to go and take the data from the earlier geostationary satellites from the late 1970s to the present time, and then create a high resolution record of precipitation, which is at 25 kilometers roughly, and covers 60 south, 60 north. I'm sorry to say that some of the northern part of the Canada is not really covered with this data set, as is true with all the satellite products usually. And the data period started from 83 to almost present. We get the data from raw data from NOAA, we process it through our algorithm and go. The algorithm actually was developed by Hamed Ashuri, who's now working either for Facebook. You know, unfortunately, good students look for other opportunities than in the field, and I guess Facebook's and others, Google's pay a lot better, as you know. So anyhow, this paper is a highly cited paper. It's called the PERSIANN-CDR. It was in the January issue of Bulletin of American Meteorological Society, and you're welcome to take a look at it. This is the page from NOAA that serves our data. A lot of people go to this particular website to get the data. So what are the capabilities of this data? Here is the Sierras of California, mountains between California and Nevada. And if I zoom into that area, I can get 7 years of historical record on a daily basis. I can take a given year and look at by months. I can take a single month and look at by day. So that represents quite a bit of data and information. For extreme analysis, you'd certainly like to have daily, if not at least monthly, but not yearly. So here is some of the features on the rain sphere. You go and you choose the different fields. There is a nice little tutorial that goes along with it. And you can essentially look at it based on rain statistics or rain trends. And you choose your watershed, you use your state, you use your country, and click on it. And within seconds, you get the data, and it shows the time series, a histogram of the precipitation pattern, say, over the state of California. And one thing you see is that despite of what everybody said, maybe you see a lot of variability, but in terms of a general trend, there is a little negative trend, but it's not statistically significant. And you can also look at a given month or year by month and days. If you go to the rain trend part of the website, you can get a picture of how our data, high resolution over oceans and over land, shows in terms of the patterns of precipitation. This is only over the continents. I'm not covering the oceans here with this graph. So you go there and you specify the period of time you want. It gives you a projection. This is from 83 to the present, and you see which parts of the world globe have seen an increase in precipitation. The cooler colors show increases in precipitation. The warmer colors show, unfortunately, decreases in precipitation. You see Northern Africa has seen, based on our almost 40 years of data, an increase in precipitation. China and others. If it's hashed, it says there's a trend, but it's not statistically significant. Unfortunately, for overall Canada, our record shows that perhaps there has been a statistically significant decrease over the entire country. But if I look at it based on the watersheds, you will see some regions have benefited from seeing increases, where certain regions, particularly the western part of Canada and some regions in the east, have seen a decrease. When you average it, that shows why we see a decrease. Colorado River Basin definitely has seen a decrease in precipitation. So enough on the climate side of things. And if I come to the iRain, which is our real-time data provider, it has also very nice features. You can just go on it and just click on it. It has different fields by which you can select your data, and it shows the time latency every 30 minutes And this one is at 4-kilometer spatial resolution, and over every 35 minutes it updates. And you can get a projection of what are the patterns of precipitation every day, every hour. And there are a lot of people that download the data. I took the liberty of yesterday, there was this major storm over the US that started 2 or 3 days ago, a lot of flooding. And I plotted it. And over the US, we have the radar information, which we have integrated. And as you see, the blue represents our estimates of precipitation observations. The green represents the radar. And as you see, we are relatively well, but some areas we don't do well, and radar doesn't do well either. Data portal is where you can go and download the data. It is, again, has a nice tutorial and tells you how you can download the data. So you wonder who uses our data. Well, there are people from 211 countries that are now registered. They come to our website, and thanks to Fu, again, he developed this website that we can monitor. We see the pattern of data download and use. And you know, there are countries like the US, private IP, we don't know who those people are, probably a commercial entity. China, Israel, Thailand, Iran, in that order are the number of visitors to our site. And we've already have over 1 million visitors, and the amount of data download is shown here. I'm coming to the end of my talk. So I talked about models, I talked about remote sensing observations. At the end of the day is how much trust can we put on these things? We have now a good number of satellites, billions of dollars of investments. These 2 satellites, the French and the Americans, measure soil moisture for us. These satellites give us precipitation. GRACE has been talked about a lot. It's the microgravity that characterizes the water column, and people have used it to interpret groundwater depletion over some regions. I usually have problem with some of those studies because the resolution of the data that is provided by this is 300 kilometers, and you try to interpolate what happens in the Central Valley of California is a little bit of a stretch. So you have all these assets at your disposal. So, but there are problems, and I am first to admit with our precipitation product, because we rely heavily on the observations from the various channels and the coldness of the clouds, etc. We are pretty good when it comes to high convective storms or cooler clouds. We capture those well. Cirrus clouds are cold, but they give you false information. You think it's raining, but it's not raining. You have warm clouds. Unfortunately, the sensitivity is less to these, but now we're making improvement. As I said, the channels have increased from 5 to 16. So that gives us the ability to try to see how we can grab those informations. Other examples of when you have to be careful. A lot of conferences you go to, there are pretty pictures like this one. This one was shown in an Australian conference some years ago by a colleague from NASA that showed the susceptibility index for landslides, and red being the highest and the yellow to being the second highest, and to blue to be lowest in terms of susceptibility to landslides. Being from Iran, it caught my eye that over the Iranian plateau, particularly at the middle of the desert, they had a susceptibility of 4. That's pretty high. So I asked the question, did you guys even look at a map of the country to see that these are all deserts and the highest thing you see is a sand dune? Why would you have such a high susceptibility? Well, since then, of course, they've changed the picture. Anyhow, my point is you always have to have a will to doubt and question the credibility of the information. Hey, so if you got tired, good news for you is my last slide. And these are personal views. I think despite advances to date, predicting the future hydroclimate variables will remain a major challenge. By the way, not hopeless, we have to work. We have to work and try to make these improvements. Why? Because our nature is complex, and observing and modeling its nonlinear behavior is extremely challenging. We should have some will to doubt the credibility of the information that is generated by the models. It's always good to question and make sure that we are on the right track. If there are deficiencies, we should acknowledge it and put the risk in there. And then I encourage that we all have to worry about long-term and sustainable observations, and which is extremely crucial, not only as input to the models, but we need to make sure that we verify models, and we need historical record to do that. At the meantime, as I said before, we just have to factor in resiliency in our water resources system design and planning, and to make sure that we don't completely miss the challenges. Thank you very much for the invitation and listening, and it was a pleasure for me to talk, and I will stop sharing and get back to see if anybody has any questions or criticisms.
Thank you very much, Dr. Soroosh. Very interesting talk covering very serious issues related to water resources. I really appreciate that.